Okay, good morning, grade nines. What we're going to do today is look at lesson 4 of our electricity unit, our physics unit. And the key here now is that we've finished chapter 10 in the textbook. We're moving on to chapter 11. The reason why I mentioned that specifically this time is because we just finished looking at static electricity. And what we're going to begin to look at today is current electricity. In other words, electricity that flows, okay, that does not stay in place, okay? So we will begin by taking a look at lesson 4, which is based on section 11.1 in the textbook, okay? And it's cells and batteries, okay? So a voltaic cell is a source of energy that generates an electric current by chemical reactions involving two different metals or metal compounds separated by a solution that is a conductor. Okay, so it's basically a chemical reaction, okay, that can generate some kind of an electric current. In other words, it can cause electrons to move through some kind of a conductor, some kind of a wire. Okay, and a guy named Alessandro Volta created the first voltaic cell. Okay, and what he did was he stacked two different metals, silver and zinc. And in between each metal, he put a piece of cloth that was soaked in salt water, okay? And that was called the voltaic stack, okay? Now, I mentioned electric circuit. What is an electric circuit? It's a closed path along which electrons that are powered by an energy source can flow. Okay, so a circuit is a closed path, okay? And through that path, electrons can flow, okay? And so in order to have that flow of electricity, you need to have some kind of source. There has to be a source of that energy. And in some cases, that source is a cell or a battery. Now, I do not want you to think of cell in the biological sense, okay? We're talking about cells in an electrical sense, okay? And a cell is the most basic component of a battery, okay? So cells and batteries are related, okay? But they are not interchangeable. One of the common misconceptions that kids make is that they interchange the word cell and the word battery, which is sometimes okay. I get what you're saying if you do that, but it's not technically true. A cell and a battery are not the same thing, and we'll talk about the difference, I believe, on the next slide. Okay, so voltaic cells. So the AA or D batteries that you might put in a flashlight, or anything, your remote control, whatever it is that you're powering with a battery, not your phone. That's not the type of battery that we're talking about. Not your PlayStation controller. That's not the type of battery we're talking about. We're talking about the batteries that you can buy, the round ones that you can put in a flashlight, okay? And other things, but a flashlight might be the most common thing that you use, although maybe you don't use flashlights anymore because you've got the flashlight on your phone. But I think we've all seen a flashlight before. If you haven't, this is a flashlight here on this slide, okay, with a battery inside of it. Looks like a D battery and a light bulb, okay? And it's connected by a circuit, okay? So this little statement here, I'd like you to correct, okay? The battery is not a voltaic cell, okay? It's actually a connection of two or more cells. So if you take a cell and you connect one cell to another cell, you begin to produce a battery, okay? So one cell is not a battery. You need more than one cell to make a battery, a usable battery. Okay. So a voltaic cell, and therefore a battery, has these components as well. But a voltaic cell, that simple unit of a cell, has two components. One is called the electrodes. And these are two metal terminals, two metal pieces. And they always have to be different metals. Okay? Always have to be different metals. And they're there to hold on to electrons. And then they must have an electrolyte. And that is some kind of a solution, some kind of a liquid or paste that could conduct electrical current, okay? In which the electrodes have to be immersed in. So if we go back, I'm going to go back again. we're going to look here at the voltaic stack that Alessandro Volta came up with. And he has the electrodes because he's got silver and zinc pieces, okay, silver and zinc pieces stacked up. And then there is an electrolyte, that's the salt water that's soaked into the cloth, okay, that he puts in between each metal, okay? Okay, so voltaic cells, they depend on a specific type of chemical reaction. And this specific type of chemical reaction, okay, involves the movement of electrons and ions that take place at the surface of each of those metal electrodes that's in contact with the electrolyte, okay? So the chemical reaction depends on which metals you pick. You can't just pick two random metals. You have to be specific about the metals that you pick, okay? But they must be different metals. In a voltaic cell that contains aluminum and copper electrodes, the aluminum is the metal that gives up electrons, and it actually gives up 3 electrons, which forms Al3 plus ions. Okay, so we talked about this in chemistry. If you lose electrons, you become positive. In this case, we're choosing aluminum because aluminum will give up 3 electrons, okay? And it'll form Al3 plus, aluminum 3 plus ions, okay? And when they form those ions, they break away from the metal, okay? So you're going to see a diagram. This is going to make sense when we look at the diagram. I think it's on the next slide, okay? What happens is, as the chemical reaction takes place, this chemical reaction that's meant to generate an electric current, okay? The metal that you begin with, the first electrode, the one that gives up the electrons, it actually decays, it actually breaks down, okay? So this is why batteries do not last forever, okay? They do not last forever. This is why batteries will run out, because one of the metals eventually will decay, okay? The electrons that are released by the aluminum, they move through some kind of a connection, some kind of a connector to the other electrode, which is the copper electrode, okay? So let's look at this diagram here. Okay. Here's the aluminum. Here's the aluminum. So what we'll see here is that the aluminum reacts with whatever this liquid is in here. Now, we haven't discussed what this liquid is or what it might be, okay? We haven't discussed what it is or what it might be, okay? But it's not just water, okay? This is some kind of a solution, which means there's some water in here, but there's some other stuff mixed in, some other stuff dissolved in here, okay? And really, just to kind of pause for a second, we are going to talk about this diagram in a very simple fashion. In grade 12 chemistry, not grade 12 physics, grade 12 chemistry, there's actually an entire unit devoted to the chemistry of these cells. It's called electrochemistry, where you're going to learn more about the metals and more about the forces that cause these electrons to move and what the solution inside the cell is made up of and how we decide that, and you'll do a little bit of math with that as well. And so there's a lot of detail that we're just going to skip over because we're going to talk about it later, and by later I mean in grade 12. Okay, so you'll have to understand that there are going to be some holes in our explanation here of the voltaic cell. Okay, and that's okay, because when we learn, and I think that you've kind of gotten this impression from some stuff I've told you before, when we learn science, we like to learn it, you know, kind of like an onion. We kind of learn it in layers, okay? So in grade 9, we give you that first layer, and then we say, okay, go learn this, okay? And it's got a certain amount of detail. And then in later years, we might peel that onion a little bit and give you the second layer of that information, okay, the second layer of that learning, and it's going to be a little bit more detail. And then we'll maybe peel another layer off, and there's going to be more detail. And that's basically how your science education is going to go for the next 8 years, should you continue on with science into post-secondary, is that you're going to continue to learn these layers of detail, So we're going to give you a very, very simple explanation of this voltaic cell now. If you're curious about learning more, well, that's going to be grade 12 chemistry. Okay, that'll be grade 12 chemistry. So basically what happens is, let's take a look at what we have in this diagram. We have two metals, okay, two metals, and they're sitting in some kind of a solution. We don't know what that solution is right now. We'll talk about it briefly on another slide. We're not going to talk about it right now. We've got these two metals. We've got aluminum, we've got copper, okay, and they're connected with this wire. The wire itself is probably made out of copper as well, okay. What happens is the aluminum, okay, reacts with whatever this solution is, whatever this liquid is, and the reaction causes the aluminum to give up electrons, and it drops off this positive aluminum ion into the solution. So what happens is the electrons, they move out of the aluminum into the copper wire, and they flow through this copper wire. And as they pass through the light bulb, okay, they give that light bulb some energy, causing it to light up. Now, why does that happen? How does that happen? That's coming up in a couple lessons, okay? What forces are causing the light bulb to actually light up? What we need to know now is the flow of electrons through that light bulb is somehow causing the light to pop up, okay? Now, the electrons pass through the light bulb, okay? And they come down, and they have to be accepted by a second metal. The electrons have to have someplace to go, okay? They must have someplace to go. And so the place that they go is into this copper electrode, this copper acceptor of those electrons, okay? And what happens here is some hydrogen ions, and it doesn't always have to be hydrogen, there could be other ions in here, but in this case, some hydrogen ions, they accept those electrons and they form H2. We know that H2, hydrogen, that's a gas. And so what we'll notice on the surface of this electrode is that bubbles begin to form, okay? Bubbles begin to form. So let's run through that again. We start with this aluminum, okay? The chemical reaction between the aluminum and this solution, this liquid, okay, causes an aluminum ion to form, okay? And it causes the electrons to pass up through this copper wire into the light bulb. When that happens, okay, the aluminum itself begins to break down because we're actually losing those aluminum ions into the solution. So if you notice in this picture, it looks kind of broken down here at this end of the aluminum. That's accurate. You will see that electrode decay. When the electrons pass through the light bulb, they'll end up at the other electrode, this time the copper electrode, where the electrons will react with the H+ ions that are already in the solution, in the liquid, and they'll form a gas, hydrogen gas, which you'll see as bubbles rising to the surface. So on one electrode, you'll witness decay. On the other, you'll notice bubbles, okay? And that whole process is to make electrons move from one metal to the other. And their motion is what causes the power in the light bulb, causes enough energy in the light bulb to turn it on, okay? So here we have two types of cells. One is the zinc carbon cell, okay? And in this case, we've got a little bit of zinc in here with a carbon rod and some kind of moist paste. I don't like saying that. It doesn't feel good, okay? But in any case, we see that we have two materials, zinc and carbon. They're going to be the electron donators and the electron acceptors. And the moist paste is going to act as the electrolyte, and that allows electrons to pass and move. And so we can power something with this zinc carbon cell. Now, you're most likely in your home, if you have batteries, you're most likely going to have an alkaline cell. And an alkaline cell, okay, let's look at what we have here. We have a steel cover at the top, okay? You've got an electrode here. It's usually called manganese dioxide and carbon. So it's a little more complicated than just one type of metal, okay? You've got the current collector. That's brass. That's a metal in there, okay? That's just to kind of like the wire. That's kind of like the copper wire that allows electrons to move. You've got a negative electrode in here. That's usually zinc. In this case, it's in powdered form. Okay. And then you've got a tube that goes all the way around that insulates it, so none of this stuff leaks out. Okay. And then if you look here, there's an electrolyte. And the electrolyte is like the liquid in the previous diagram. Okay. In this case, it's potassium hydroxide. Okay. So do we have two electrodes? Yes. We've got manganese dioxide and carbon as one electrode. We've got zinc as our second electrode. And then we've got this potassium hydroxide that represents the electrolyte that allows a chemical reaction to take place so electrons can move. Okay. So dry cells use an electrolyte that's paste. That's why we call them dry cells. Okay. These are both dry cells. Okay. And we like dry cells because if we damage them, we don't have a lot of leakage that happens. Okay. Wet cells, okay, they contain some kind of liquid electrolyte. And a lot of the times that liquid is sulfuric acid, which of course is corrosive. It burns. Okay, it's very cheap to use, but it burns. There is a type of battery that we use very commonly that has sulfuric acid. That's a wet cell, and that's a car battery. Okay, and so if you ever end up working on a car, or you own a car, or you're working on a car with your parents, and there's something wrong with the battery, sometimes you'll see that sulfuric acid leak out. That's a very bad sign that you need a new battery. You must be very, 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 very careful. You should not touch it because that sulfuric acid will corrode your skin. It will burn your skin. Okay, but we use it in cars because it's a very good battery. Okay, it's a strong battery. Okay, so it's dangerous, but we use it, and we use both of these types. You probably know that you use the dry cells that look like this. You probably didn't know that you use a wet cell in your car because you don't drive, and why would you have ever looked? But you do. Okay. Okay. Cells are also classified depending on whether they can be recharged. So primary cells, they can only be used once. Okay. So for example, your typical battery, you use it, it gets used up, and then you dispose of it responsibly. That does not mean you throw it in the garbage. That means you take it to like a Best Buy or a Staples Business Depot, and they have proper battery disposal areas. I think even the city dump has an appropriate place for you to drop off used batteries. So there are a number of places. Make sure you Google it before you throw any batteries out again. We don't want them going into the garbage. Okay, they're very toxic for the ground. Okay, a secondary cell is one that can be recharged. Okay, so what we do when we recharge a battery is we take that electric current. We know that there's a specific direction in which that electric current goes, right? We know there's a direction that it has to go in. Okay, and what we do is we reverse the electric current. Okay. And we reverse it by actually reversing the chemical reaction. And what that does is it restores the cell to its full capacity. Okay. So the battery that we use in a car, which I have here in the corner, okay, that's a secondary cell because we can actually charge the battery. Now, have you ever charged a car battery before? Well, no, because you don't drive. But basically what happens is when you want to start the car, when you have to start your car or run any of the electrical equipment in the car, the radio is a good example. The GPS device gets built into the dashboard of your car. If you're using the plug in your car to charge your phone, that's drawing power from the battery. Okay. When you run the engine, the lights as well, the lights are the big drain on the battery as well. If you leave your lights on in your car without the car engine on, you will drain the battery. Okay. When you drive the car, when you use the engine of the car actually charges the battery itself. Okay. So driving the car charges the battery. Using the equipment in the car, like the stereo and the lights, that drains the battery. Sometimes you can drain your battery by leaving your lights on or leaving the radio on or something like that for too long, like the light up inside the car, if you turn that on and you forget to turn it off, you might wake up the next morning and find that the car battery is dead and the car won't start. Then you've got to take jumper cables to the battery and attach them to a second car and jump the battery. That process reverses the chemical reaction as well and recharges the battery just a little bit. Okay? So here is a big table of all the different types of batteries we might use. Okay? So zinc carbon, alkaline, silver oxide, zinc, I'm not going to read all of these. What I'm going to ask you to do is I'm going to ask you to read this table. Okay, so pause the video if you're watching the video, or just take a look at the slide because you have the PowerPoint itself, and make sure that you're familiarizing yourself with the different types of batteries and kind of say, hey, where in my life do I use this battery? Okay, where do I use this battery? What are the benefits of using this battery? What are the downsides of using this battery? Okay, and you can see here the one we've been talking about a lot, the lead acid battery. That's a car battery. Okay. What's the benefit of the car battery? It delivers a high current, it's cheap, okay? What's the con? What's heavy? And it has a hugely corrosive sulfuric acid electrolyte, okay? So take a look at that. That's something you can do independently. I think there might have been some homework questions that may reference this chart for you to take a look at, but this is a good thing to kind of have in front of you and not memorize, but just kind of make yourself familiar with, okay? And that's it for today. So that actually, for